Now let's discuss queues. A queue is a very broad concept. The stack concept we discussed earlier, or the linked list, these are also considered as different types of queues. We call these different queuing disciplines. So a queuing discipline actually defines how and where a new item is inserted and how and from where an item to be taken is removed from the data structure. But what we are going to discuss in this section will be the specific queuing discipline, which is called FIFO, first in, first out, or another name is also first come, first served, FCFS. FIFO is a more commonly used term, but as I said, in this section, we will be specifically looking at FIFO queues. So when I say queue, I mean a FIFO queue. So a queue in the broadest sense is a data structure to which a newly coming element is appended from the end. And when an item is to be taken from the queue, it's taken from the front. This is very similar to what we experience in our daily lives. For example, when you go to a bank or the cantina, you get in the line. So that line is actually a FIFO queue. So the first person who comes to the cantina is at the front of the queue. The person who comes next will be behind the first person, and the third one will be behind the second, and the fourth one will be behind the third. When someone is to get the service, it will be the first person in the queue. After that person is served, the next person is getting the service. That's why it's called first in, first out, or first come, first served. So we're going to talk about two specific methods or operations. One is called enqueuing, which is actually putting or storing an item in the queue, and the dequeuing, which is removing or retrieving an item from the queue. So the general representation of queue is like this. So the newly coming items enter from here, and this is the first item that goes into the queue. The next one goes behind that, and the next one. Remember, in the case of a stack, we would be removing item C. However, in the case of a queue, when an item is to be removed, this is the beginning or the head of the queue. So the first one to be removed will be A. So B will be shifted into the place of A. So it will be removed from here. And C will be shifted here and removed from here. Therefore, the last item is gone. So the size of the queue has diminished by 1 when one gets service. So enqueue operation is putting an item in this queue, and dequeue operation is removing the head from the queue. So the notation we're going to use will be, again, we will be representing the data structure, this time Q with the letter Q. E will be the item that's to be stored or removed from the queue, and B is a Boolean value. So we can define now the primitives like initialize Q, which will just create an empty queue for us. Queue empty method will check if the queue is empty or not. Queue full will check if the queue is full or not. Now, this queue full method makes sense when we have a limited size for the queue. So we have an upper bound for the size of the queue. You could define a queue to have infinite size, But in reality, of course, there will always be a limit for the size of the queue. So the NQ and DQ methods will be implemented this way. NQ will put E in the queue that will be appended to the end of the queue, and DQ will remove an element from the head of the queue. So let's look at a couple of simple problems. Let's try to implement a new method or procedure which will take two parameters, Q and P, and append all elements in P to the end of Q in the same order, and the elements will be removed from P. So the idea is actually remove the elements one by one from the Q and append it to the end of the other one. So for example, you could consider P to be like this and Q as another Q. Say in P we had 1, 2, 3, and in A we had A, B, C, and D. Let me make this longer. So the idea is to copy everything from P to Q, and these get placed at the end of Q, but in the order they were in P, and these elements will be removed from here. That's what we want. So try to solve this algorithm just as an exercise. Actually, it's quite easy. I will not give the algorithm in a written manner here, but just let me explain in words. Let's go back to the original case. So what we are going to do is we are going to dequeue the elements from P one by one and enqueue them into P. Now, could I do it in a while loop like while P is not empty, E becomes what we get from P. So, or let me write it this way, dequeue from P, or let me correct it. Earlier we wrote it this way. So dequeue from P, the element you get, write it into variable E. Okay. So what happens now is I have a variable E. When I dequeue from P, remember, the first element will be removed from here, so I write it here. But when you do that, second element moves here, third moves here, and this is decreased by 1. And then enqueue into Q, the second Q, that element that you have removed from P. So remember, it puts at the end, so it will write it here. And this loop will repeat. So this time it will remove 2 from here. 3 will be written here. And then you enqueue to Q. The P is not empty at the moment. So again, remove 3, write it in 3. Now P is empty, but wait, I didn't come to the check yet. Let me execute the second instruction in the loop body. So enqueue, which means write it here. And now come to P. Is P empty? Yes. So the predicate here saying P is not empty is false. Therefore, it will terminate, and we have an empty P, and Q contains all elements P appended to the end in that order. Let's now look at another problem. Now, we're going to write a procedure that will reverse all elements in Q. So whatever Q was, it will contain the elements in the reverse order. For example, you were given a Q which contained, let's say, A, B, C, D. After your method is executed, Q will be modified as D, C, B, and A. So how can we implement such a method? Let's see. For example, think about the following. Very similar to what we did earlier. While Q is not empty, I'm going to remove one element from Q and put it in variable E, and then enqueue this into Q. Let's see if it works. Let's see if it will do as we planned. The first element will be D instead of A. So this is, remember, this is what we want at the end. Let's keep it on the side. So we start with this Q where A is the first element, D is the last element, and we have a variable E. Take one element from Q, so you're going to take A from Q. So this is removed. A comes here. B will be shifted. All elements actually will be, shifted. And the last one will be gone. And then the element that we removed, the one in E, will be enqueued to Q. So when you put it, it goes, remember, when you say enqueue, it goes to the end. Okay, so A is not lost. It has moved to the end. Now this looks similar to what we wanted earlier, right? Okay, seems like I'm going in the correct manner. Let's see. Now come back. Q is not empty. Okay, so remove B and put it in the variable and shift all elements. And then enqueue B. Okay, and repeat this. So C will be removed from here and do the shifting and enqueue that new element. Now remove D and do the shifting and enqueue D. I got the original. So what I did was I was removing the last element from the right and putting it from the left. When I do this 4 times, actually I just shift everything by one position 4 times and I get the original one. What's worse, does my algorithm stop here? No, because Q is not empty. Okay, and this will continue forever. It will continue forever, so it's an infinite loop. What's more important, you never get what we wanted. So this definitely was not the correct approach. So you should think about some other solution. So remember, for this, we want 2 different solutions. One is a non-recursive algorithm. There you're allowed to use a stack. And the second approach is a recursive algorithm. Then you're supposed to do it without using a stack. Our precondition is that we're given a queue which is initialized. And post condition, the condition after our algorithm terminates, is that all elements in the queue should be in the reverse order. So let's first look at the first solution. which is non-recursive, and you're using a stack. So Q was like this, and I'm going to create a stack. Let me call that stack S. Q was initialized as before, let's say. So while Q is not empty, remove an element and put it in the stack. So there is a variable E, but I'm not going to show it. I'm just trying to be a little bit faster. So put A here, and everybody gets shifted. Q is not empty. So again, remove one element, B. So remember, we have B in hand, and we have shifted these, and push B into the stack S. Remember, it always comes at the top. Remember, the stack was actually a pile of like plates. So since Q is still not empty, we're going to remove this time C and put it in the stack, and then remove D and put it in the stack. Now Q is empty, so the first while loop terminates. I have an empty loop, empty Q, and everything is in the stack. At the top, I have D. Now remember how the stack works. When you try to remove an element, you remove from the top. So we start the second loop now. And while the stack is not empty, which is not, take the top element using pop. So you're going to remove D from the stack and enqueue it in Q. Since Q is empty, D will become the first element. Stack is still not empty, so remove C and enqueue. Pop B, enqueue. Pop A, enqueue. And now the stack is empty, so the second loop also terminates. The whole method ends, and you see that the elements in Q have been reversed. What's the complexity of this one? Well, this part worked with complexity ON. Then I had another ON complexity. So the overall complexity would be ON plus ON. Note that it's not ON inside ON because these two loops are not nested one another. Therefore, it would be O2N, which is equivalent to ON. How about the alternative solution, which implements the recursive algorithm? Here we're going to implement the recursive solution under the method name reverse Q, which takes a parameter with the name Q. So I'm going to explain this example here using the call stack. So this is the call stack used by Java when you're calling the methods. Remember, at the bottom you have main method. So let it remain there. And we're at a point, say from the main method, we're calling this reverse Q method. Also, an object has been created for this FIFO Q with the name Q. And let's assume it was already initialized in the main method to contain the values A, B, C, D. Okay, so we call the reverse Q method. I will just write it in short this way. We call the reverse Q method by passing the reference to this Q. So in the reverse Q method, we have a variable E. So I will create a variable E here. So in the first invocation of the reverse Q method, we call the Q on Q. So it will remove the first element of Q, which is A, and put it in the variable E. And of course, shift all elements. Sorry. And here, recursively call the reverse Q method once again. So although the previous invocation of reverse Q is not finished, we call reverse Q once again. Remember, this is what we did with recursive methods. So this second invocation has its own copy of the variable E. It starts from the beginning, it comes to this if statement, and Q is not empty. So it will dequeue the first element, which is B. So remove B, write it in this variable, and shift the elements in the queue. Note that when we copied the first element to the variable E here, the value B, the previous invocation was still preserving its own variable E, so nothing happened to that one. That's the idea in recursion. And again, at this point, we call reverse Q once again, so yet another invocation of reverse Q occurs with its own copy of variable E. And again, you dequeue one element from the queue, that will be the value C, and shift D to this position. And once again, recursively call reverse Q, so yet another call for reverse Q, which has its own copy of E. And the Q is not empty, so it will remove this element, copy it here, and recursively call reverse Q. So yet another invocation of reverse Q occurs. Of course, that also has its own copy of E, but the moment it starts the method, this statement says if not Q empty Q, well, this time it's empty. Therefore, it will just not enter the then part, and it will exit the if statement and come to return here, which means this is the end of this invocation. So it has not done anything actually there. So this invocation of reverse Q ends. So it's removed from the call stack, and we continue with the previous invocation, which is this one. This time from the next instruction, which is NQ. So what's the value in E? It's D in this invocation. This is the last invocation. So from here, it will take D and put it in Q. Q was empty, so D will be the first element. And that's also the end of this invocation. So you come to return. Therefore, that's the end of this invocation. So this will all be removed. So we continue with where we were left in the previous invocation. For the invocation where the content of E was C, so again, put C in the queue. There's the element D there. So C comes after D. And that's the end of this invocation. So again, remove these. Continue from where you were left in the previous invocation. So NQB, and that's the end of this invocation. And finally, we continue with the first invocation of reverse Q method, which was actually invoked from the main method. So it will NQ A, and that would be the end of all invocations of reverse Q method, and we are left with the Q that contains the values A, B, C, D, but this time in the reverse order. D is the first one, then C, then B, then A. So now let's look at another example. Again, we have two queues with the names P and Q. We want to append all contents of P to the end of Q, leaving P empty, but they should be appended in the reverse order. So you're given the problem where P and Q are already initialized. They could be empty or not. And Q contains all elements originally in Q, followed by all elements in P, but in the reverse order. The order of the elements in Q will not change, but the order of the elements in P will be just the inverse. And when we are done, P also should be empty. So try to design a recursive solution to this one as an exercise. This is the end of this section and also the chapter. We have here some previous exam questions that will help you to study also.